Today we're going to explore one of the most elegant and counterintuitive problems in microfluidics: how staggered herringbone mixers achieve exponential mixing at extremely low Reynolds numbers. Let me start by framing the problem. Imagine you're trying to mix two fluids in a tiny channel, maybe 100 micrometers wide. What do you think happens when you try to mix them? At the microscale, turbulence essentially disappears. The flow becomes completely laminar. Two streams flowing side by side will just stay side by side, barely mixing at all. This is quantified by the Reynolds number, which is the ratio of inertial forces to viscous forces. At low Reynolds numbers, viscous forces dominate completely. The Reynolds number equals density times velocity times characteristic length divided by viscosity. In microchannels, this number is typically between 0.1 and 10. Here's what happens in a straight microchannel. Red and blue fluids flow side by side, but they don't mix. They just form laminar streams that remain parallel. The only mechanism for mixing is molecular diffusion, which is extremely slow. It can take minutes or even hours to achieve good mixing. The diffusion timescales as length squared divided by the diffusion coefficient. For a 100 micrometer channel, with typical aqueous diffusion coefficients around 10 to the negative 10 meters squared per second, this gives mixing times of tens of seconds. So here's the key question: how can we dramatically speed up mixing when we can't rely on turbulence? The answer is chaotic advection. The staggered herringbone mixer was invented by Stroke and colleagues at MIT in 2002. It's a passive mixer that creates chaotic flow patterns using only geometric features. Here's what the mixer looks like. It consists of diagonal grooves etched into the floor of a microchannel. The grooves are arranged in a herringbone pattern that alternates or staggers every half cycle. The grooves are typically 30 to 50 micrometers deep, which is a significant fraction of the channel height, usually around 100 micrometers. Now let's understand the physics. When fluid flows over these diagonal grooves, something remarkable happens. The grooves generate transverse flows perpendicular to the main flow direction. The grooves create counter-rotating vortices in the cross-section of the channel. These vortices circulate fluid from top to bottom and side to side. You might wonder, why do diagonal grooves create these circular vortices? It comes down to the no-slip boundary condition and flow continuity. Near the channel floor, the fluid must follow the groove direction because of the no-slip boundary condition. The grooves force the fluid to move diagonally. But fluid can't just disappear. Conservation of mass requires that if fluid moves in one direction near the bottom, there must be return flow elsewhere in the channel. Here's the genius of the design. The herringbone pattern is staggered. After half a cycle, the groove orientation switches. Why is this so important? When the pattern staggers, the rotation direction of the vortices reverses. This creates a stretching and folding motion that is the hallmark of chaotic mixing. Let me explain why stretching and folding is so powerful. Imagine you have a blob of red fluid and blue fluid. In the first half cycle, the vortices stretch the blob, elongating it into a thin sheet. This increases the interfacial area between red and blue. Then when the pattern staggers, the vortices reverse direction and fold the sheet back on its. Now you have multiple layers. Here's the key insight. Each stretch and fold cycle approximately doubles the number of layers. After n cycles, you have roughly 2 to the n layers. The number of layers grows as 2 to the power n, where n is the number of cycles. This is exponential growth. After just a few cycles, you go from one blob to many thin interleaved layers. The interfacial area increases exponentially. To understand how fast mixing occurs, we need to introduce the Peclet number. This dimensionless number compares advection to diffusion. The Peclet number equals velocity times length scale divided by diffusion coefficient. It tells us whether transport is dominated by flow or diffusion. At high Peclet numbers, advection dominates and diffusion is relatively slow. In microfluidics, Peclet numbers are typically between 100 and 10,000. Let's work through a concrete example with real numbers to see how powerful this mixing is. Typical conditions: velocity 1 millimeter per second, channel width 100 micrometers, diffusion coefficient 10 to the negative 10 meters squared per second. The Peclet number is 10 to the negative 3 times 10 to the negative 4 divided by 10 to the negative 10, which equals 1,000. This is quite high. Without any chaotic mixing, the diffusion time across the channel would be L squared over D, which is about 100 seconds. But with the staggered herringbone mixer, after just 5 cycles, we have 2 to the 5 equals 32 layers. The striation thickness is now 100 divided by 32, roughly 3 micrometers. Now diffusion only needs to act over 3 micrometers, so the mixing time drops to about 0.9 seconds. That's more than 100 times faster. There's a beautiful mathematical analogy that helps explain this mixing. It's called the baker's transformation, and it's literally about making pastry. Imagine you're making croissant dough. You start with a layer of butter and a layer of dough. First you roll it out, stretching it to twice its original length. Now it's thinner. Then you cut it in half and stack one piece on top of the other. You're back to the original size, but now you have 2 layers of each. Each time you repeat this process, you double the number of layers. After infolds, you have 2 to the n layers. This is exactly what the herringbone mixer does to fluids. This is the baker's transformation. Stretch, then fold. The herringbone mixer does this continuously as fluid flows through. For those interested in the rigorous mathematics, the exponential growth of mixing is quantified by something called the Lyapunov exponent. The Lyapunov exponent lambda equals the limit as t goes to infinity of 1 over t times the natural log of the distance between trajectories at time t divided by initial distance. A positive Lyapunov exponent indicates chaos. Nearby fluid elements separate exponentially fast. For effective herringbone mixers, lambda is typically between 0.1 and 1 per cycle. Let's discuss the key design parameters that determine how well a staggered herringbone mixer works. Groove depth should be 30 to 50% of the channel height. Too shallow and the vortices are weak. Too deep and they don't span the full channel. The groove angle is typically 45 degrees relative to the flow direction. This balances transverse flow strength with pressure drop. Each half cycle should be about 1 to 2 channel widths long. This gives the vortices time to develop but switches before they decay. The aspect ratio of groove width to ridge width should be close to 1. Equal widths give the strongest and most symmetric vortices. Let me emphasize again why the staggered pattern is absolutely critical. Without staggering, you don't get exponential mixing. If the grooves all pointed the same direction, you just get steady rotating vortices. Fluid would go in circles, but layers wouldn't multiply. This staggered pattern with periodic reversal is what creates both stretching and folding. This is essential for exponential growth of interfacial area. Non-staggered grooves create circular motion without folding. Staggered grooves create the stretch and fold pattern with exponential layer growth. How do we know this actually works? There have been beautiful experiments using fluorescent dyes to visualize the mixing. Researchers inject fluorescent dye into one of the fluid streams and use a microscope to watch what happens as it flows through the mixer. After just 3 to 5 herringbone cycles, the fluorescence becomes nearly uniform across the channel. The initially separated streams are completely mixed. Typical results show mixing efficiencies greater than 95% in residence times well under 1 second. Compare this to minutes in a straight channel. You might ask, is there a fundamental limit to how fast we can mix? What's the theoretical best performance? The ultimate limit is set by molecular diffusion. You still need to wait for molecules to diffuse across the final striation thickness. The minimum mixing time scales as 1 over Peclet number times the advection time. For PE equals 1000, you can achieve mixing about 1000 times faster than pure diffusion. Well-designed staggered herringbone mixers achieve 80 to 90% of this theoretical maximum. That's remarkably efficient. These mixers have found applications across many fields. Let me mention a few important ones. Lab-on-a-chip devices use them to rapidly mix samples with reagents for medical diagnostics. Fast mixing enables faster results. In chemical synthesis, they enable precise control of mixing times, which is critical for controlling reaction selectivity and yield. For nanoparticle synthesis, rapid mixing creates uniform conditions that produce nanoparticles with very narrow size distributions. In protein folding studies, researchers use them to rapidly change solution conditions and watch how proteins respond in milliseconds. The concept has been extended beyond the original design. One elegant variation is the 3-dimensional serpentine channel. Instead of grooves on the floor, the entire channel winds in 3 dimensions. This creates chaotic particle trajectories without needing surface structures. The advantage is easier fabrication. You don't need to etch fine grooves. The disadvantage is the device takes up more space. One practical consideration is pressure drop. Do the grooves significantly increase the pressure needed to drive flow? The pressure drop increases with a factor that depends on the groove depth d over channel height h. The coefficient alpha is typically around 2. For typical designs with groove depth 30% of channel height, the pressure drop increases by about 20 to 40% compared to a smooth channel. This is a modest increase and is acceptable for most applications, especially given the enormous improvement in mixing performance. Let's discuss how mixer performance scales with channel size and flow conditions. The number of cycles needed for complete mixing scales logarithmically with Peclet number. This is because of the exponential growth. You need log base 2 of PE cycles. For Peclet number 1000, log base 2 of 1000 is about 10. So you need roughly 10 mixing cycles for complete mixing. If you double the channel width, you double the Peclet number, but you only need 1 additional cycle. The logarithmic scaling is very favorable. It's worth comparing passive mixers like the SHM to active mixers that use external energy input. Active mixers use magnetic stirrers, acoustic waves, or electric fields to directly force mixing. They can be faster but require external power and control. The staggered herringbone mixer requires no external power, has no moving parts, and is highly reliable. It's purely geometry driven. For most microfluidic applications, passive mixers like the SHM are preferred because of their simplicity and reliability. A quick word on fabrication. How do you actually make these tiny groove structures? The most common method is soft lithography using PDMS, which is polydimethyl siloxane. You create a master mold using photolithography, then cast PDMS against it. For larger devices, you can use direct machining or even 3D printing. The key requirement is sufficient resolution to create the groove features. Typical groove widths are 30 to 50 micrometers, which is achievable with standard microfabrication techniques. There's been extensive research on optimizing the groove geometry. The original design used simple chevron patterns, but refinements have been made. Asymmetric groove patterns, where one arm of the chevron is longer than the other, can enhance mixing by creating stronger asymmetry in the flow. Using multiple groove depths in sequence, gradually decreasing, can optimize the progression from large-scale to fine-scale mixing. Performance is quantified using a mixing index, which is 1 minus the standard deviation of concentration divided by the initial standard deviation. For the mathematically inclined, the complete description involves solving the advection diffusion equation in the channel. The concentration C evolves according to partial C, partial T, plus velocity dot gradient C equals d Laplacian C. This is the advection diffusion equation. The velocity field has 3 components created by the grooves. The transverse and vertical components are what create the chaotic mixing. To simulate the mixer, you must solve the coupled Navier-Stokes equations for the flow field and then the advection diffusion equation for the concentration. The ratio of channel width to height significantly affects mixer performance. Wide, shallow channels with aspect ratios of 5 to 10 provide stronger transverse mixing because the grooves can influence a larger fraction of the flow. Square cross-section channels are more symmetric but generally show weaker mixing because the vortices have less leverage. The optimal aspect ratio is typically between 3 and 5, balancing mixing efficiency with fabrication constraints. Let me summarize why staggered herringbone mixers achieve such remarkable performance at low Reynolds numbers. The key principle is chaotic advection. The grooves create a stretch and fold motion that rapidly increases interfacial area. The number of layers grows exponentially as 2 to the power n. This exponential growth overcomes the slow diffusion at low Reynolds numbers. The mixer is completely passive, requiring no external energy beyond the pressure driving the flow. The geometry does all the work. Practical devices achieve mixing times 50 to 100 times faster than pure diffusion, making second-scale mixing possible where it would otherwise take minutes. This is a beautiful example of how understanding fundamental physics enables elegant engineering solutions. At low Reynolds numbers, inertia is negligible, and flow is time reversible. This seems like a limitation, but we turned it into an advantage. Static geometric features create persistent, predictable flow patterns. We exploited this to engineer chaos in a controlled way. The result is counterintuitive. Exponential mixing without any turbulence, achieved through purely geometric means.